But yeah, next up, Melih from DNV, and there you are. I'm looking forward to hearing what you have to say.
Is this okay now? Yeah. Oop. Real loud. Yeah. Armin and Yoon already presented you the SeaZero project, so you have familiarity. How can I reduce the volume a bit? Yeah. Okay. Thank you. So in this presentation, I will be just focusing on one milestone methodology and results. And this is about testing the autodocking functionality of the SeaZero project vessel. And in this research, we collaborated with Brunvoll, Ward, Hurtigruten, and Sintef. So we had some initial meetings with the Hurtigruten seafarers, captains, and we decided a quite challenging task, which is docking to Brunøysund quayside. And as you can see, it's approximately 4 nautical miles of travel through a quite narrow channel, and the bathymetry is also quite shallow. And when we investigate the environmental forces, we realize that the wind and the current are significantly from north and south directions. And you can see the wind is approximately maximum wind speed is around 15 meters per second, and the current is around 2 knots maximum. So we will use this information when we are testing the system. And from this map, you can see, maybe it's hard to see, but the depth information is also important when testing these systems. And we have approximately between 7 and 30 meters of depth in this area, in the last leg of docking operation. And yeah, we have two main objectives. The first one is identifying the performance criteria when we are testing this auto-docking functionality. And the second objective is to find some efficient methods to test these systems. We want to aim for efficiency, which means fewer simulations and getting the maximum informative results. Yeah, I think in this room, many people are familiar with the STC, Simulation Trust Center, developed by the DNV. And we use the knowledge and experience from the OSP project. And basically, yeah, sharing the FMU models to STC platform. One of the main functionality of this STC platform is that you can, in a secure way, share your models, model exchange functionality. And partners can set different access levels to these models. So you cannot download, maybe you can just use it in your simulations and to protect the IPR. And the system integrator connects them and creates a complex system. And then you run the simulation, the time domain simulation to get some results. So in this milestone, we use the Brunvoll models, Brunvoll FMUs. You can see we have a vessel model. The main FMU is the controller FMU, which has the path following and the auto-docking functionality. And we also have a captain FMU, which is a high-level mission planner. And we have a set of thrusters and the sensor FMUs. So the heart of the smart testing is about the methodology that we use. We are talking about complex systems with many different configuration parameters. And when you combine these configuration parameters, you end up with a large search space. It can be hyperdimensional search space. And the traditional approaches rely on the random sampling or uniform sampling or factorial designs. They can be infeasible when you have large search spaces. And as I mentioned, we aim for the efficiency and to identify these failure or edge cases. And for that, we use an adaptive sampling methodology. And in this work, we use the Bayesian optimization using the Gaussian processes. And we call it in short smart testing. This is the search space that we defined for this research. So you can see that we discretize the wind and the current directions and the speeds. Even these simplified versions, we end up with almost 25,000 test cases, different combinations. So aiming for the full coverage or random sampling, you need to run thousands of simulations to get some meaningful information. And spoiler effect alert, sorry, we run only 40 simulations to identify these critical cases in our initial tests. So these are the results from our first objective, identifying the evaluation criteria. We sat down together with the partners, and we discussed about which evaluation criteria we need to monitor to test the performance of the autodocking system. The first one is, of course, the most important. We want to be sure that the vessel is not grounding. The next three of them is about trajectory following performance, cross-track distance, heading error, and also speed tracking errors. And the final two are related to the final position of the vessel. When the autodocking operation is finalized, we want to be sure that the vessel is close to the docking position, and the heading of the vessel is also in alignment with the planned heading. So to use these evaluation criteria in the optimization algorithm, we are using single temporal logic, as we just discussed about it. Basically, we need a scalar value. And the single temporal logic gives us this robustness score, which is showing how much you deviate from your requirement or how much you met your requirement criteria. And we use this temporal operator, as Haytham mentioned, the global operator. Here it's called always operator, the square one. And basically we are checking throughout the simulations, we want to keep all the evaluation criteria within defined limitations. So we also hear about the surrogate model throughout different presentations. And Bayesian optimization using the Gaussian processes relies on this surrogate modeling. And you can use different methodologies to create a surrogate model. But in this Bayesian optimization using the Gaussian processes, of course, using the Gaussian processes. So we have a set of Gaussian distributed functions with some uncertainties. And the Bayesian optimization uses the acquisition function to optimize minimizes the uncertainty regions. And this action is actually the adaptive sampling part of the algorithm. And this translates into our new test cases throughout the simulations. So for that, we use the X platform. It's developed by Meta. And we, of course, has to work on it to create, to integrate to our simulation platforms, STC, and also our smart testing setup. And especially, we wanted to use a multi-objective approach. So we use the multi-objective Bayesian optimization algorithm supplied from this platform. So the multi-objective approach enables us to evaluate the 6 evaluation criteria at the same time to create this Pareto front, which means the critical test cases. I mentioned about 40 simulations. We start with the 15 random sampling method, and this gives us the base for the surrogate model initialization. And after the first 15 simulations or trials, we continue with the Bayesian optimization. Yes, some results. So this is an animation how the algorithm explores and exploits the search space. If you look at the trial numbers, the first 15 of them are randomly sampled. So you can see the distribution around the search space. But after the 15, the Bayesian optimization starts to exploit the system. And you can see, especially in the current ocean current diagram, the algorithm starts to exploit from a certain region around the northwest. And this is a quite important and informative information for us, because from the initial tests with only 40 simulations, we start to identify the critical regions, and we communicated with the Brunvoll to tune the model and improve the performance of the models. And this is another diagram from the robustness scores, so 6 evaluation criteria. I put a dashed line to show you which part is the random sampled and which one is the Bayesian optimization. So you can, from the graph, you can see the initial 15 simulations, the performance is better than the rest of the 25. That shows that the Bayesian optimization starts to identify these critical regions to exploit the system and degrade the performance. So just additional information. +1 means the good result, and -1 means the bad result, and 0 means right on the boundary. This is just one example from the 40 simulations. In this case, we have the wind from 160 degrees with 1 knots and current from 220 degrees from 0.8 knots. And a visualization from the STC. So you have the dashed lines as a planned trajectory and the dotted lines as the real final trajectory. And the vessel navigates through the narrow channel and then finally initiates the docking procedure from the starboard side. And I have a final slide with, one more. This is just to show that the controller for the reference speed and the heading is performing quite well. It follows the reference signals. And this is a final demonstration of that same example simulation, showing in an animation. Maybe I can fast forward a bit. So vessel navigates through the narrow channel and approaches to the port side. I have to run it in 20x to reduce the speed, to reduce the time of this animation. Yeah, I think this is also quite important to have these visuals to identify and debugging. So throughout the collaboration phase, we run many simulations before starting this smart testing setup. And these many simulations, you need to go back to plot these results to see some meaningful behavior. Yes. To conclude, in this work, we identify 6 evaluation criteria that we believe we can use it also for the future autodocking testing. And we demonstrated an efficient testing strategy using the design of experiments and adaptive sampling. And we also experienced the importance of the co-simulation and collaboration between the partners. So both the Brunvoll also improved their system controllers by using our inputs, our feedbacks. At the same time, we improved our STC, adding new features from their feedbacks. Yeah, we believe this is a good way forward for testing autonomous and complex systems. Thank you very much for listening. And yeah, happy to answer any questions.
Well, Melih, you make me look like a donkey, because on a magical mystery tour, I was very proud about the review article we wrote about simulation-based optimization and adaptive stress testing. I mentioned signal temporal logic, and I didn't say this, but we concluded our review of the literature when it comes to optimization by saying Bayesian optimization looks promising. I was all up high on my research horse, feeling good about myself, and then you come and demonstrate we do all that stuff already, which of course is awesome, because then the magical mystery tour bus has actually landed. So
awesome. But also we are exploring different methodologies. This is just one of them, and like we want to come up with set of tool set for design of experiments. Like we are also investigating evolutionary algorithms to come up with many simulations and see how it progresses. But of course, both have different pros and cons. Bayesian optimization enables us to have heavier simulations with fewer simulations, but maybe our hypothesis that the evolutionary algorithm might be also important to aim for coverage in the search space.
Yeah, love to continue that conversation
afterwards.
Good stuff. Sorry for hijacking the question round, but this was interesting.
There is some questions in the back.
I'm wondering if you have heard about or looked at the hybrid evolutionary algorithm from Filippo Sanfilippo
No.
for PID controller, no?
No, actually, I would like to have a look a bit more. At the moment, we use the some traditional NCGA3 evolutionary algorithm for many optimization problems. But I would like to learn a bit more about that, maybe in the after this session. Yeah.
One more.
Thank you for the presentations. I just want to ask, because you mentioned that you have like you mentioned about the tendencies of like the current and then like the wind speed, but I want to ask if is there any like a probability distribution for it, because I'm actually working with adaptive stress testing as well. And like adaptive stress testing also works with maximizing the likelihood of the, like the actions, for example. So if you've been wondering how to reduce the search space, you could also actually try to look for the likelihood of those, environmental loads. That's what I'm actually working on as well.
Yes,
so,
I think that's a good way. We had the chance to have some domain experts, like the Hurtigruten captains who sailed in that region, and also some previous work from the environmental data source. So from those work, they identified that the north and the south directions are the most significant, and we don't really have any important or significant wave height in the region. And for like if you don't have that kind of information available, I think it's also useful to, if you don't have these experts in your resources, it's important to use the statistical methods to identify.
I mean, maybe if there's like a seasonal data, for example, it is useful because, for example, like I'm using reinforcement learning, and you use those likelihood to create the reward designs, the reward signals or the reward functions. Because like if you think about like probability, it is like between 0 and 1, but you can turn it into like a log probability, and then the value will becomes like 0 to negative infinity, and like for those unlikely event, it will be like negative infinity, and it's like it can be like a really insightful information for the reinforcement learning agent to kind of cut down all of those unnecessary, like unimportant environmental, and that maybe can help.
Yes.
Yeah.
Yeah, we should continue discussion. Yeah.
Okay, thank you.
Thanks. Yeah. I guess we're coming to an end. The pizza is here.
Well, we're coming again with the
You have to turn on your mic, by the way.